Dear colleagues, scientists, friends, it's my pleasure to welcome you at the lecture of the Alfred Wegener Medal of EGU 2019. I am Alberto Montanari. It's an honor for me, it's a privilege to chair this session. Medal lectures, as you know, have the purpose of presenting to the community the best achievements of our union medalists. Actually, as you know, the medal was already awarded to the winner on Wednesday during the medal ceremony, so today's session is dedicated to the medal lecture. The Alfred Wegener Medal of EGU is associated with the honorary membership. And it's a medal that celebrates and recognizes the achievements of outstanding scientists in atmospheric sciences, hydrology, and ocean sciences in their widest sense. In the past, in EGU, we called the group of these disciplines soft earth to identify and distinguish them from the solid earth. Today, we are embracing a more interdisciplinary vision, and we know that everything that is related to atmospheric sciences, ocean sciences, and hydrology, ideally is to be related within an interdisciplinary context. This year, the medal is awarded to Michael Bender from Princeton University. He is the kind of scientist that I think brilliantly put together these disciplines that are recognized by the Wegener Medal and are a part also of the work of Alfred Wegener. I say that because the activity of Michael Bender has been, in my view, truly interdisciplinary. He devoted attention to carbon mitigation, climate science and modeling, Earth history, environmental chemistry, and oceanography within a very broad vision. In fact, the citation reads that the medal is awarded to him for groundbreaking contribution to understanding the history of atmospheric composition. So I think it's really an ideal vision in interdisciplinary context that characterized the whole his activity. Michael Bender received already many recognition. He is fellow of the American Geophysical Union. He's a fellow of the Geochemical Society. He was awarded the Patterson Medal by the Geochemical Society. He's a member of the National Academy of Sciences of the United States, and he was awarded the Revell Medal by the American Geophysical Union. So you see that indeed his vision has been recognized by several associations at the very global level. So I'm very pleased that today we are also recognizing the merit of his contribution within the context of the European Geosciences Union, so that you might indeed become an ambassador of geosciences at the very global level. Now I think it's time to give the word to the speaker for this exciting medal lecture, and therefore I'm inviting Michael Bender on the floor, please.
Thank you very much for those kind remarks.
I forgot my phone, you know.
I was going to call you.
It's here.
Okay, thanks. When I found out that I'd received this medal, I started doing some reading about Wegener's life. And there's one story I'd like to tell you, and that is that Wegener was primarily an atmospheric physicist. And as part of his work, he and his brother, who was also an atmospheric physicist, got access to a hot air balloon, loaded it up with devices for making atmospheric measurements, threw in provisions for themselves that included 2 liters of sparkling water, a kilogram of chocolate, 2 bananas, and 4 smoked pork chops. And they climbed into the wagon and took off. They came down about 48 hours later, and the reason they had to come down or else they were going to get blown out over the ocean, before they came down, they tried to make one more vertical ascent and descent, but they couldn't do it because they were too weak to throw the ballast bags over the side. So reading stories like this made me feel a little adventurous. And some of the things that I decided to talk to you about are a little outside my own comfort limit, but they're things that I've been thinking about recently, and I hope that you find them interesting. I'm going to start off with some brief background, which is intended to give context for people who don't usually think about the oceans. And then I'll talk about some factors influencing net community production in the oceans, which is essentially a photosynthesis in excess of respiration. So it's the amount of carbon left over from photosynthesis after losses due to respiration. I'll talk about the role of variability and irradiance in influencing net community production, the role of respiration itself, and the cycling of nutrient-poor organic matter between the mixed layer and the underlying waters. What I'm going to discuss doesn't mean that any of our estimates of net community production have changed or are going to change. It's just that I'd like to give some visibility to topics governing net community production that maybe we haven't thought as much as we would benefit from. I'm going to talk specifically about measuring net community production in the South Pacific subtropical gyre, which is interesting because it's a region of very low productivity. And then I'll talk about the observation that the range of variability in net community production in the world's oceans is small, and why that is, why there's not more variability. Okay, so this is, by way of background, the diagram on your left plots temperature on the x-axis and the water depth on the y-axis. And then this line is meant to indicate observations. So typically, temperature will be constant throughout the first top 50 meters of the water column. This is because down to some depth, tens of meters, winds at the surface induce mixing of the water column and keep it homogeneous. And this mixing happens rapidly. For example, on a windy day, the mixed layer will completely turn over multiple times. And then below some depth, which may be typically is 50 meters, at lower depths, temperatures decrease with depth. The waters become denser and denser as they get to be colder and colder. So vertical mixing is rapid in the mixed layer, but because of the density gradient, it's slow below the mixed layer. The light penetrates in the oceans typically with a lot of variability, but typically to a depth of about 100 meters. And so the 100 meters is a typical measure of the bottom of the euphotic zone. Above that, there's light more and more as you get closer to the surface. Below that, it's dark. And this is a highly generic plot of the concentration of biologically active chemicals versus water depth. Nutrients dissolved in organic carbon, metals used by organisms, for example, increase with depth. And the reason is that nutrients in organic and inorganic carbon are assimilated at shallow depths where there's sunlight, and they're released by respiration or remineralization at deeper depths. This gradient, these low concentrations at shallow depths, are one signature of net community production, because if you have a lot of net community production, the phytoplankton take up all the carbon and nutrients in the sunlit region of the oceans, and their concentrations are low. Okay, so first thing I want to talk about is light variations in primary production. We typically think of the surface as receiving a certain amount of radiation, which depends on latitude, on the season, and on cloudiness. And then we think of respiration as we think of sunlight of insolation as decreasing progressively with depth below the surface according to an exponential e to the minus kz. And these exponential terms, k is a measure of how fast light decreases with depth, and z is the depth below the surface. If light intensity is varying, then photosynthesis rates by phytoplankton will also vary, of course. There are several reasons why light intensity at a given depth can vary during the day. One is that there's vertical mixing within the mixed layer, for example. So if 50-meter mixed layer would be associated with a factor of 10 decrease in irradiance from 100% at the surface to 10% of surface irradiance at 50 meters depth. So as mixed layer waters are actively convecting, phytoplankton are continuously seeing changes in irradiance. Second thing is clouds, whose influence on irradiance is obvious. And the third thing is refraction of sunlight by waves. So if you go to the beach in the summertime and you stand in the water and look down at the surface, it's mottled. And that modeling, that variability comes from refraction of light, which can influence the light field to tens of meters below the surface in the clear open ocean. From my reading, it seems that fluctuations that are shorter than a second or so enhance productivity, and I don't really have a good feeling for why this is. But fluctuations in irradiance longer than a second tend to diminish productivity. And what this, the reason for that is that phytoplankton like to become acclimated to a certain intensity of sunlight. If you change that intensity, then they have to kind of make physiological changes to try to catch up to the new irradiance, and their photosynthesis will be deficient while that acclimation is occurring. So for example, on a perfectly cloudless day, if the winds are still, phytoplankton will tend to have high productivity because there will be no mixing or little mixing in the mixed layer because of no winds. And as a result, their irradiance will be constant. On the other hand, during a windy day, when the mixed layer is actively convecting, phytoplankton will be trying to catch up with the changing irradiance, and their productivity will be lower. This is actually something we should be able to observe. The differences from experiments that have been published might be on the order of 20% or so. So they're quite large. Second thing I want to talk about is respiration. And the interest here is that for reasons that you'll see, phytoplankton lose a huge amount, 40% or more of the carbon they fix to their own respiration. And I want to go over where that number comes from and why these losses are so large. So these blue arrows here are meant to represent the photosynthetic apparatus. An atom with a molecule with 3 carbon atoms enters into, These arrows are meant to represent the respiratory apparatus of plants and phytoplankton. A molecule with 3 carbon atoms, a 3-carbon molecule, enters into this complex. And first thing that happens is through interactions with this enzyme, it loses one of its 3 carbon atoms, which is lopped off, broken off as carbon dioxide. So, and then we're left with a 2-carbon molecule. This 2-carbon molecule combines with a 4-carbon molecule to make a 6-carbon molecule. And then that 6-carbon molecule undergoes several rearrangements until it becomes 6-carbon oxalosuccinate. This molecule gets transformed to a 5-carbon atom with the loss of a second CO2 molecule. Then in the dark, this 5-carbon molecule loses another of its carbons and becomes a 4-carbon molecule, which gets transformed to oxaloacetate, which reacts with this 2-carbon molecule to produce this 6-carbon molecule, and the whole thing goes around again. So in one cycle, this 3-carbon molecule enters, it loses 1 CO2, 2 CO2s, all 3 CO2s, and of course energy is produced in that process. And this is what happens during the night. During the day, things may be similar in this part of the cycle. Again, this 5-carbon molecule alpha-ketoglutarate is produced, but in the day, the 5-carbon molecule tends to interact with ammonia to gain a nitrogen atom, and we're left with a 5-carbon atom that now has a nitrogen atom added to it. That molecule is glutamate, and plants essentially stop at this point or use glutamate to make other amino acids. So in the daytime, only 2 carbons from this original 3-carbon molecule lose CO2, and we get 2 CO2s and a glutamate. Phytoplankton typically have a carbon to nitrogen ratio of 7 carbon atoms to 1 nitrogen atom. And I'd like you to think about this as the formula for a molecule. So imagine a molecule that represents marine organic matter with 7 carbon atoms and 1 nitrogen atom. How much respiration, how much CO2 release will we have when that molecule is produced? To do this, I need to tell you one more thing, and that's that based on observations, which show a huge amount of scatter, but based on observations, rates in this part of the cycle tend to be the same in the day and in the light and in the dark, in the day and at night. And we're going to use that fact in the calculation that's coming up. So we're going to make a 7-carbon atom, 7-carbon molecule that also has a nitrogen. To do this, in order to fix the nitrogen, we have to break off 2 CO2 molecules. And what I'm referring to is to fix 1 nitrogen atom, we lose a CO2 molecule here, and we lose a second CO2 molecule here. Oops. And that will happen during the day. Nitrogen tends to get fixed mostly in daylight. But then during the following night, we're going to lose another 3 carbon atoms to CO2 by the process of respiration. And those 3 carbon molecules are this CO2 that comes from this 3-carbon compound, the CO2 that's lost at this point, and the CO2 that's lost at this point. So to assimilate one nitrogen atom, we produce 2 CO2 molecules during the day, and we produce 3 CO2 molecules at night from the respiratory cycle. And in order to respire these 5 CO2 molecules, we have to fix 5 molecules of organic carbon from CO2 to start off with. So what's happening is that during the day, phytoplankton fix 5 carbon molecules that are going to be consumed in respiration. In the daylight, they respire 2 of those carbon molecules to 2 of those carbon atoms to fix 1 nitrogen atom. During the following night, they respire 3 more carbon atoms as CO2, and they also need, during the day, to assimilate the carbon that they're going to respire at night. So it sounds like a futile cycle, but of course what they're doing is harnessing sun's energy and using it to make ATP. So the overall balance of carbon is that 7 carbon atoms go to new biomass to make our 7 carbon atom molecule. 5 carbons will be assimilated and respired to carbon dioxide. So we need to assimilate a total of 12 molecules of carbon dioxide, 5 of which will be lost to respiration, and 7 of which will remain for the new carbon molecule that we're making. And so the ratio of respiration to photosynthesis is 42% in this simple example. There are other ways that you can work this problem and get a smaller answer or a larger answer, but the point is that for respiration that's associated with nitrogen fixation or that's just part of the plant's energy requirements, a large fraction of the carbon fix needs to be remineralized. And this is something that limits net community production because obviously if you're recycling on the order of half the carbon that you fix, there's a limit to how fast net community production can be. Okay, now for a long time, there's been a conundrum associated with the observation that in the central gyres of the ocean, which are nutrient-poor areas of the ocean, in the central gyres of the ocean, there are extremely low concentrations of nutrients, but there's relatively high rates of net community production. So how is this possible? And these rates, which turn out to be quite significant oceanographically, are on the order of 2 to 3 moles of dissolved inorganic carbon assimilated into from dissolved inorganic carbon assimilated into organic carbon per meter squared of ocean surface per year. And one factor, so the question is, with hardly any nutrients in the water, how do you make all this organic matter? So one idea that's been proposed is that phytoplankton make dissolved inorganic carbon that has a very low concentration of nutrients. Another thing that clearly contributes to this problem is that when you don't have any fixed nitrogen in waters in the euphotic zone, phytoplankton do nitrogen fixation. And both of these things contribute to the issue, but they seem quantitatively insufficient to account for most of this production of organic carbon or net community production. So another idea that's been proposed is that large phytoplankton, which are big enough that they can sink at significant rates, sink down from the surface waters of the ocean to 100 meters depth or more, where there are significant concentrations of nitrate. They kind of load up their cytoplasm with nitrate, become positively buoyant, float back up to the surface, and they release their nitrate to the surface ecosystems where it's consumed extremely rapidly, keeping the nitrate concentrations very low. This mechanism too likely contributes to carbon fluxes, but there are two concerns that I at least have with it. The first is that there's remineralization of organic carbon at shallow depths, which is presumably the carbon that's fixed in the surface water, sinks down a little bit into the dark ocean and is remineralized. And in this remineralization process, CO2 is released, but our observations are that only CO2 is released and nutrients are not released. So the implication is that this cycling is just cycling of carbohydrates. It's not cycling of nitrogen compounds. And to repeat, the reason we think that is that below the sunlit ocean, where remineralization takes place, there's an interval where only CO2 is added, but no nitrate. Whereas nitrate would be added if nitrogen-rich organic matter were being remineralized. So, and then the second concern I have about the vertical migration hypothesis is that there are going to be carbon fluxes associated with vertical migration, just like there are nitrogen fluxes. And these carbon fluxes are likely to be larger than the nitrogen fluxes. For example, carbon will be lost to respiration. And this carbon loss to respiration is likely to be greater than the carbon fixation associated with the transport of nitrate from the dark ocean up to the surface ocean. So another hypothesis has been suggested, and this has been developed recently by Sarah Fawcett and Danny Sigmund and their colleagues. And the idea is based on the observation that in the sunlight, if there's no nitrogen around, phytoplankton just tend to produce carbohydrates. Carbohydrates that have carbon, hydrogen, and oxygen, obviously, but have essentially no nitrogen. So their idea is that you make carbohydrates, you excrete these carbohydrates, and after excretion, they glom together to form a compound called transparent exopolymer, TEP. And then the TEPs, so there's fixation of organic carbon, but instead of the carbon that's produced being transformed into an essential biological compound, it's just a marginal compound that's excreted. And then this TEP agglomerates and sinks down and is released in the aphotic zone of the oceans. And so this is a hypothesis that explains the surface drawdown, and it also explains the fact that carbon is remineralized below the euphotic zone with very little nitrogen associated with the remineralization. A limitation of the TEP hypothesis is that the density of TEP is very low. It's about 0.75 to 0.8. So if you want to get TEP to sink, you have to mix it with ballast. The only plausible source of ballast, given the carbon fluxes, is calcium carbonate. And we know what the calcium carbonate flux is out of the euphotic zone. We know the TEP flux that we need to satisfy the carbon balance observed from dissolved inorganic carbon fluxes. And it turns out that there is enough calcium carbonate to mix with TEP, form a compound that has a density greater than 1 and will sink down, but kind of just barely enough. So for calcium carbonate to account for most of the to provide the ballast for most of the downward flux of TEP, you have to mix pretty much the perfect proportions of calcium carbonate and TEP so that on the one hand, you don't run out of calcium carbonate too quickly, and on the other hand, you get rid of all the TEP. And maybe it works, this is how the system works, but it's a little troubling. So I've become intrigued with the idea that starch, which is a polymer of glucose, may be important in this process. And the basic idea is again, based on Fawcett and Sigmund, that the flux of carbon is just associated with uptake of carbohydrates in the surface and the burning of carbohydrates and their conversion to CO2 at depth. But the compound that's involved is starch. Starch has a density of 1.6, and so it solves the buoyancy problem. There's as I said, phytoplankton in nitrogen-limited waters in the presence of sunlight tend to produce large amounts of carbohydrates. And perhaps foremost among these carbohydrates is starch. And in the lab, you can get phytoplankton, which are tenths of % by weight starch. So clearly, there's the potential for producing large amounts of starch. An historical note, there was an 1880 paper by Gyres in which he proposed that phytoplankton in the shallow ocean produce starch during the day. They become negatively buoyant, sink down, and burn their starch at night. And when they burn their starch, they become positively buoyant because they lose this dense material and they float back up to the surface. We now know that it can't be this simple because phytoplankton are too small for the most part to migrate vertically, but this may, Gyres' idea kind of may provide a hint. So there are two ways that starch could work to give us this flux. One is its association with vertically migrating phytoplankton or rhizoselenium mats, and the idea there is that starch could be produced in the mixed layer, agglomerated into large enough assemblages of phytoplankton that they sink down and burn their starch and come up to the surface. So it's essentially the Gyres hypothesis, but with the formation somehow of sinking aggregates that won't just float in the surface water. And the second possibility is that export production includes substantial amounts of phytoplankton with high concentrations of starch. And with high concentrations of starch, and when these phytoplankton are exported out of the euphotic zone, they will carry their starch down to the dark oceans, burn it by respiration, and release the CO2 in that way. I have to say, there are a lot of people who are leaving. I think it's perfectly appropriate because the subject matter of this talk is not for everyone. And honestly, I've discouraged a number of my friends from coming here. Hopefully that didn't work. But anyway, you've had a sampling, and if it's not to your taste, I'd be really appreciative if you leave now, and if you stay, I hope you'll stay to the end of the talk, because it's somewhat disconcerting. Okay, so I want to turn now to the measurement. Oh, and one other thing, I understand people have to leave because of logistics, so that's something else. So I want to turn now to net community production, and I'm interested. There are the way net community production works in different parts of the oceans, the way we measure it in different parts of the oceans. varies from one area to another. I'm going to talk about just one case, and that is the subtropical South Pacific gyre. And the reason I chose this is that this region is the most oligotrophic, the lowest nutrient, the lowest chlorophyll region of the planet. And I was interested in getting a robust estimate of net community production there. So this is a global map showing the distribution of chlorophyll in the sea surface. Hot colors are high chlorophyll concentrations, cold colors are low chlorophyll concentrations. And what you can see, there are the central regions of the North Pacific, South Pacific, North Atlantic, South Atlantic oceans, which are very low chlorophyll, highly depleted in nutrients. And the question I want to ask is whether this particular region, kind of the eastern subtropical South Pacific, has lower productivities than other regions of the ocean. So let's start with these data. This is a plot of temperature versus depth. It's just like the plot I showed you at the beginning of the talk. The temperature is constant down to a few tens of meters of depth. That zone is the mixed layer, and then temperature decreases with depth and density increases with depth. This is apparent oxygen utilization. The way I'd like you to think about this plot is going in this direction indicates supersaturation. Numbers that are less than 0 are supersaturated in oxygen. Numbers greater than 0 are undersaturated in oxygen. So this region is supersaturated in oxygen. It means that there must be a certain measurable amount of net community production, photosynthetic production of O2 greater than respiration. And so as you go in this direction, you're going towards higher productivity, or at least more photosynthetic oxygen dissolved in the water. And then this shows the concentration of dissolved inorganic carbon normalized to a constant salinity. And what you can see here is something that will look unusual to those of you who've thought about data like this before. Normally, when one plots the concentration of dissolved inorganic carbon versus depth, one sees constant concentration in the mixed layer and then increasing concentration below the mixed layer. Here, what we see is constant concentration in the mixed layer and decreasing concentration below the mixed layer, and then concentration starts increasing. So this is something I've worked on with my colleague, Boer Johnson. Our interpretation is that there's very little net community production in the euphotic zone, essentially no CO2 drawdown during, in the mixed layer, there's no CO2 drawdown during the growing season. Below the mixed layer, there is drawdown of dissolved inorganic carbon. The abundance of phytoplankton is so low that there's plenty of sunlight penetrating down to deeper depths, and as a result, the uptake of dissolved inorganic carbon occurs not in the mixed layer, where it's most intense everywhere else in the world's oceans, but below the mixed layer. Below the mixed layer, perhaps because these waters are closer to the nutricline, although you don't get any measurable nitrate until you get down to about 200 meters depth. So now what we can do is integrate this area in here and compute the amount of CO2 drawdown that has occurred during the growing season. And that's shown in this plot here. The CO2 drawdown is, during the growing season is just represented by this box marking off the missing dissolved inorganic carbon. And the area of this box calculates to summertime drawdown of dissolved inorganic carbon of about 1 mole per meter squared over the year's growing season. So if you remember, I said that Bermuda was 2 to 3, and the global range turns out to be somewhere from 1 to 5, or close to 1 to 5, and this is an indication for lower, the least the most chlorophyll-poor region of the ocean having significant drawdown rates at the kind of the lower end of rates of other areas of the world's oceans. This is another way of coming up with the same estimate of net community production in the subtropical South Pacific gyre. There was one SOCOM float deployed that went up and down measuring the nitrate, the oxygen concentration, along with nitrate actually and other properties. And this is a plot of those data. Time in both of these plots goes from January 2017, January 2018, and 2019, so time goes in this direction. Depth goes in this direction, 0 to 300 meters in both of these plots. And this plot shows temperature, and this plot shows the oxygen supersaturation. So what I want to point out is that during the growing season, which in the southern hemisphere, the mixed layer gets deeper and deeper every year, of course. And then below the mixed layer, in this zone of increasing density and low, vertical mixing, oxygen just accumulates. So if you look over the course of a growing season, you see the oxygen supersaturation, which is what's plotted here, getting higher and higher and higher and higher. And this increase in oxygen during the growing season is the quantitative mark of net community production. The higher net community production, the more oxygen remains behind in the water column. So from this increase in net community production, and the thickness of the zone over which this increase is manifested, we can calculate net community production in this region, and we get a value of about 0.7 moles per meter squared per year. So we're left with the observation for which I've shown you one line of evidence, we've looked at just one area. We're left with the observation that net community production over the global ocean is about 1 to 4 moles per meter squared per year. And this range includes fluxes from the Southern Ocean, Equatorial Pacific, North and South Atlantic, North and South Pacific, the Eastern tropical, subtropical South Pacific, which we've just been talking about, although maybe it's a little lower there. And so the question is, why is this range not larger? So there are a number of factors that I'm going to mention. The first is shown here by this map. This map shows average irradiance over the Earth to orient you. Here's North America, South America, Africa, Europe, and Asia and Australia, Pacific, Atlantic Ocean. And what you can, and then the colors, hotter colors indicate higher average irradiance. And what I'd like to point out is that in the low latitudes, the average irradiance is on the order of 250 watts per meter squared. In the high latitudes, it's lower, of course, but it's only lower by about a factor of 2. So it's 125 watts per meter squared. So, you know, we tend to think of the tropics as being much brighter than high latitude waters, and of course they are, but the difference is limited. It's about a factor of 2. It's not like a factor of 10 or something like that. This plot shows the surface water nitrate concentration, and again, cold colors indicate low nitrate, hot colors indicate high nitrate. And what you can see is that nitrate is very low in the central areas of the oceans, and it's very high in the high northern latitudes and the high southern latitudes. So the nutrient abundance is exactly the opposite of the light availability. And this is a second factor that will tend to even out productivity of different regions. Where light is high, nutrient concentrations are low, and where light is low, nutrient concentrations are high. And this is kind of a summary of these and other factors that influence net community production and tend to buffer regional variability. So low latitude areas, because they're warm, tend to have high rates of gross production and lower ratios of net production over gross production. High latitude nutrient-rich areas are nutrient replete, or at least nitrogen and phosphorus replete, but they're not all that fertile because the growing season tends to be short in high latitudes. Iron is frequently limiting, and self-shading due to high abundance of phytoplankton limits how far light can penetrate in the water column. And then low-latitude nutrient-poor regions, despite their paucity of nutrients, tend to be moderately fertile because the biomass is low, light penetrates deeply into the water column. The low nutrient levels inhibit microbial consumption of dissolved organic carbon, so you don't tend to cycle dissolved organic carbon very rapidly. There's nitrogen fixation, which of course alleviates nitrogen, the limitation of fixed nitrogen. Migrating organisms, as we talked about before, have the ability at least to bring nutrients in from deeper waters into the euphotic zone. Organisms can lop off phosphorus atoms and perhaps nitrogen atoms from dissolved organic carbon, so they can generate nutrients without affecting carbon fluxes. And finally, in low-latitude nutrient-poor waters, there's a cryptic carbon cycle allowing for mixed-layer carbon export via carbohydrates. And what I mean by cryptic carbon cycle is this kind of ephemeral feature of the oceans where phytoplankton appear to make carbohydrates. Those carbohydrates somehow find their way into the dark oceans where they're rapidly consumed. And so the system is spinning, but this is not a process that will lead phytoplankton to divide and multiply. It's just sitting there going around for lack of anything better to do. Thank you.
Thank you, Mike, for this indeed very inspiring presentation. I'm now opening the floor for questions from the audience, if any. And if you have any question, please go to the microphone because we are web streaming and therefore we need also to record the questions. Please.
I have a question. I'm a soil scientist, so I don't know anything about what you're talking about. But there are two areas that I'm curious. And one is your discussion has involved a lot of comments about nitrate. And I'm a little bit surprised. I would have thought that all the organic N that's being mineralized would be accumulating as ammonium N. Okay, so that's one question. And so I'm surprised that it is as nitrate. The second one is that you were looking for a ballast for your transparent exopolymer. And I was wondering if clay minerals floating about in the water might be a potential ballast.
Okay. Well, you know, as a foreigner, I really appreciate your coming here and hearing what I had to say. First of all, you're right about ammonia. All nitrogen from decaying organisms is excreted either as dissolved organic nitrogen or as ammonia. It turns out that there are bacteria who figured out a way to make energy by oxidizing ammonia to nitrate. And in most areas of the oceans, this oxidation happens very quickly. So most fixed nitrogen is present as nitrate. There's some nitrite, and of course, there's also a little bit of ammonia, but nitrate is the dominant nitrogen source. And then the second question, can you say again what that was? Oh, yeah, why can't clay minerals form as serve as ballast? They do, but the flux of calcium carbonate out of the upper oceans is on the order of 5 to 10 times the clay mineral flux. And the sinking flux of clay minerals undoubtedly is somewhat associated with TEP, but it's not enough to remove anywhere near the amount that's required.
We have time for, please to the microphone, thank you. We have 2 questions, so once at a time, please.
In the paleoclimate, what role did net productivity play in regulating or changing the CO2 concentration in the atmosphere, and what role might it play in the future?
Let's see. What net community production is it takes dissolved inorganic carbon, which is a source of CO2 to the atmosphere. That word source is not the best way to think about it, but forgive me. But anyway, take dissolved inorganic carbon, which is a source of CO2 to the atmosphere, and you package that dissolved inorganic carbon by net community production into particulate organic matter. And that particular organic matter sinks down. So you have, as a result of net community production, you have less dissolved inorganic carbon in the surface ocean, which, after you think about CO2 equilibrium, means you have less, you have a lower partial pressure of CO2 at the sea surface and in the atmosphere. So what net community production does is it removes carbon from the mixed layer where that carbon could elevate the atmospheric oxygen concentration. If you poisoned all life in the oceans, then the dissolved inorganic carbon concentration of surface waters would rise. And it's been a long time since I thought about this, but I think atmospheric partial pressure of CO2 goes up to something like 700 or 800 parts per million. In terms of the future, as I understand it, the thinking is that the ocean will be more stratified. That will make it harder to get nutrients to the surface. And as a result, net community production will be lower. So that would provide a positive feedback where the ocean is less efficient at taking up CO2. But you also need to worry about the mixing between the mix of mixed layer waters down into the ocean. I think it acts as a positive feedback, but what comes out of the models, I'm really not sure.
So generally, respiration increases faster with temperature than photosynthesis. So have you thought about those effects at the mid and high latitudes as the temperatures warm, according to what you were just saying, in the future, to net community production?
Well, yeah, so the role of, yeah, I mean, that's a really frustrating question because most phytoplankton, people have done experiments on phytoplankton in the lab, and maybe somebody in the audience is familiar with such work, but I don't recall well, I guess there are some experiments where people have looked at phytoplankton in systematic ways. Maybe you should tell us what...
Well, my look at the literature is they don't look at the effects separately. They look at growth rate or net productivity, and so they don't look at respiration and photosynthesis separately, which is something probably we need to do a little bit more carefully.
And then, let's see. Oh, and then in the oceans, you know, you can't, I don't know how you would observe phytoplankton respiration in the oceans because the respiration is due to the whole community, and a lot of it is heterotrophic.
Okay, thank you once again, Mike. Thank you to the audience for the attendance and above all the questions. I'm now closing the 2019 Alfred Wegener Medal Lecture. Once again, Michael, on behalf of the audience and the EGU Council, congratulations. Thank you.